Okay, hello everyone. Well, welcome to version 13's release. So it's exciting to be here again, talking about a new version of Wolfram Language and Mathematica. It's been just a bit over 6 months since the last minor version, 12.3, except it isn't so minor, came out. Now we're talking about version 13.0. It's been a couple of years since version 12 came out. Over the course of that time, we've added a huge amount of new material. Essentially, what we try to do is that the 0.1 releases, a couple per year, are intended to pick up all of the R&D that we do during that period of time. And then the big integer releases are ones where we get to finish stories on lots of kinds of things. Now, it's kind of interesting to see the progression over the years that we've been able to add in each major release, progressively more new functionality. In the current release of version 13 relative to version 12, we were added about 600, let's see, what is it? 635 new functions. And to give a sense of scale, in version 1 of Mathematica and Wolfram Language back in 1988, the total number of functions was 554. So between version 12 and version 13, we've added more new functions than the total number of functions that were in version 1 of the system. And the thing that those new functions that we add today are much bigger, stronger things than a single new function was a third of a century ago when we first released version 1. What we get to do as we build a new function today is build on top of all the things that we've created so far. And that means that the kinds of things that represent one new function today tend to be bigger, stronger, more powerful things than they ever were in the past. And also, one of the things that we've done a lot of work to achieve is maintain coherence and unity to our whole system, which means when we add a new function today, it has to be knitted together with everything else that already existed. Now, today we're releasing version 13. There's a whole bunch of 1.3s going on here. It happens to be the 13th of the month. That was largely coincidental. It's also been 1/3 of a century. It was about a month ago. It was 1/3 of a century since the first release of Mathematica and Wolfram Language back in June of 1988. So it's been very satisfying and impressive to see what's happened over the last third of a century. It's we went from the computer industry is probably 2/3 of a century old. The first commercial computers came into existence about 2/3 of a century ago. We have existed with our system for half of that time. And during that time, the kind of vision that we've had for what Wolfram Language and Mathematica should be has, well, it started in a good place and it's continued evolving from there. And we were able to start from this foundation of our computational language, our symbolic programming environment, and we're able to build more and more on top of that. In fact, the thing that has been impressive to me and which I've been understanding recently, particularly in the context of a bunch of new basic science that I've been doing, is just how remarkably successful and in a sense, how much it was sort of a good core choice to base our whole system on this idea of symbolic expressions and transformations of symbolic expressions. And then over the years, to understand how much we could put sort of all the computational knowledge of the world into this system and build out this whole idea of computational language. All right, so what I want to do here is show you a bit of what's new in version 13.0. And I'm mostly going to concentrate on what's new in 13.0 relative to 12.3. If I were to talk about the whole version 12 to version 13 transition, that's even more to talk about. And I will say that I just posted today, just now, a piece about what is in version 13 here. So you can find this piece, and I'll be more or less going through what I've discussed in this piece as we go forward here. So let me without further ado, concentrate on the on what we can do here. So let me okay. So this word cloud kind of gives us some indication of some of the new features in version 13. I'll be talking about this long, you can see the thumb is very small there. I'll be talking about this long post of all these different kinds of things that are in version 13, showing them, and then there'll be an opportunity for Q&A afterwards. Please feel free to ask things on the live stream, and I'll try and address them. That's what we're going to look at. So this is kind of an interesting summary plot here of how much was new in successive versions of our system. And you can see that version 13 has more that is new relative to version 12 than we've ever had new in a version before. And you can also see this kind of very steady drumbeat of innovation and delivery of technology that we've had now for many, many versions, and that we expect to continue into the future, and that is made possible by the whole platform and set of capabilities that we've built. All right, well, let's get started here, and let's actually look at some of what's new. So there are many different areas that we can talk about. I should say, by the way, that everything I'm showing here is available right now. It is available to download for desktop versions. It is also available in the Wolfram cloud, and in fact, the cloud version was updated a few days ago. You can, if you go to the cloud, you can be running all the same things I'm talking about. I'll probably post the notebook that I'm making in the cloud, so you can play with it as you wish. All right, so let's talk about what's new, and we're going to go over lots and lots of different areas. Let's start off with an area that was big a third of a century ago. When we released Mathematica, from its very name, it was clear that this sort of the killer application area was mathematics. Clearly, we've expanded far beyond that. Mathematics was a great place to start, but the core structure of the Wolfram language was always intended to support the kind of whole spectrum of computational X fields, not specifically mathematics, but we continue to advance in terms of what can be done mathematically. And one of the things that was a neat feature back in version 1 was we can do integrals symbolically. So here, for example, we're getting, this is a particular integral, and this is something that we couldn't do before, and now, hopefully, we can do it. It's remarkable that even after all these years, there are advances to be made in the art of symbolic integration. Not only in which integrals can be done, but sort of the big challenge is when you do an integral, can you get the result of the integral in some form that humans like? And that's something, again, that we've been able to achieve here. So another thing that we've done has to do with mathematical functions. Back when one did integrals by hand, one of the things I always used to like is, you do an integral, and when you do it by hand, then it's like, oh, I want to show you before I do anything else, I want to show you a new feature which we're not going to get to see as I go further, because the notifier that comes up won't come up again after the first time in a session. Okay, so this is one of the things we're always trying to kind of smooth and polish the ways that people can make use of our system and make use of our notebook technology. So let me show you one that's a new thing. So I type F and I type open bracket, and look, it typed a closed bracket at the same time. Oh, you know what? I'm too late here. There's a notifier that comes up the very first time in a session that you type this, but I was going to show you the notifier, but I already told the notifier to go away. So it's not going to show me that again in this session. And you can tell it to go away for all sessions. Once you've seen it once, you don't need to see it again. But it is explaining how you deal with this idea of you've typed an open bracket. Now I can type a G here, type an open bracket, it'll type a closed bracket. I type a brace, it'll type a closed brace. But how do I get out of here? And the whole idea is you can type an arrow if you want to, but you can also just type through the bracket. So in other words, when the bracket is there and it was automatically added, if you just type, if you just respond to what the computer already added for you, and you type the same thing again. So I type H, I type the open bracket, and now it's typed a closed bracket, and I'm now going to press the closed bracket key again, and it's going to type through the closed bracket. So this is kind of the idea. It's like things are generically matched brackets. That's really useful, but the way that you kind of move through that is you type the things you would have typed before, but even if you didn't want to bother to type it, you can just click outside and you will have matching brackets. Okay, coming back to what I was talking about before, one of the things that was always exciting when back in those days when I used to do things like integrals by hand was when you would do some integral and you would realize that that integral came out in terms of some mathematical function that one hadn't heard of before, and so on, and that was kind of always always an interesting thing. And in a sense, these mathematical special functions are kind of a way of packaging different kinds of mathematical knowledge. So to know that this is a trilogarithm function is to know that along with this idea of the trilogarithm, you get this whole sort of package of mathematical knowledge about the way that about what that means. So in any case, one of the things that that there's a kind of a zoo of these mathematical special functions, this sort of packaging of mathematical knowledge, hundreds of these things. And it was always the case that there were a couple of well-known handbooks about mathematical functions. One of them here to show you it. One of them was this book, Abramowitz and Stegen. It's a book about mathematical functions, and it has a combination of formulas and actual numerical tables of those functions. Well, when we were first building Wolfram language and Mathematica, the thing that was kind of, this was one of the books that we used as sort of the benchmark reference for mathematical functions. And so one of the questions is, do we have everything now? Are we there yet? Did we finish putting all the mathematical functions from Abramowitz and Stegen into the system? And the answer is, as of version 13, we are done now. We have every function that is in the Abramowitz and Stegen book is now in Wolfram language. And that's a plot that you could find on a page of Abramowitz and Stegen. I don't know quite why that plot range is given explicitly there, but why is it coming up with this notifier? This should not be there. This is a mistake in something. But anyway, but what we can see is that's the plot in the handbook. And of course, now we can go and do a larger range of that plot and see more. I guess it gets more difficult to compute the further you go. That gets to be a very big function. Maybe we could just do a log plot just for fun, just see what it does. Oh, that's exciting. Oh yeah, it went negative there. And so I guess we could do just for fun. Let's just do a plot of the log of these things, and let's do a just for fun, let's do a re-im plot of that, just to show the real imaginary parts. Re-im plot was a feature of oh, it's taking it. Oh, there we go. That's kind of cool. Okay, so there are the imaginary parts of which are in this case rather trivial, but that's kind of a fun thing to see. All right. So mathematical functions, we've tied a little bow there. That's exciting to see. Now, let's see. Boy, there are already questions on our live stream, questions about optimizations for Macs with the M1 chipset. There are some things, there's more things being worked on there. It's a very new technology. The first step is to get everything to actually work correctly, which we believe it does. And the next step is to start optimizing things. So question from Peter, do brackets autocomplete at all levels? The answer is yes, but it is complicated what the heuristics are for when brackets will autocomplete, because there are cases where you don't want them to automatically complete, and that has to be handled. As a question, I suspect from oh boy, people are asking for the font to be even bigger. All right, let's go even bigger here. Maybe should we go even bigger still? I think if we go even bigger still, there'll be very little that can be seen on the screen at one time. Although maybe I should just make this window bigger, and let's go ahead and set. Let's see, we're at 200%. Yeah, okay, this is good. JR is asking, does our software support customizability or enhanceability? It's a computational language. It's a language for specifying anything computationally. So the answer is very dramatically yes. And actually also, it's a system which for the very beginning, a third of a century ago, we kind of make the decision that the user can modify anything. And it gives you various protections against doing things, but if you really want to, you can make 2 + 2 be 5, although it will try and persuade you not to do that. I will say there's one new feature that's coming in this version, which is in our so-called Paclet system, the ability to customize the lots and lots of different things is coming. Okay, let's launch further. All right, next new thing I want to talk about is about numbers. How could there be something new to discuss with numbers? This notifier, I have to figure out how to get this not to come up. Okay. Let's say we want to compute pi squared to 50 digits. Okay, great. We've got that. This is an approximate real number that is represented to that amount of precision. So when we do a computation on it, let's say we say what is the I don't know, the nearest integer to that. We'll get an exact number, but this is an approximate number represented to a certain precision, with the idea that some true real number is this number to this number of digits plus fuzz to additional digits. Now, one of the things that we did in version 12 was to add this concept of around. So around, this is going to drive me crazy. Just a minute. Okay, so around has this idea. So you can type in a number like 4.5, and you can say 4.5 with an error of 1.2. So that's 4.5 plus or minus 1.2. And if I work out what's the square of that number, it will correctly keep track of the error in that number. And here this was a slightly trickier case to format because the error was in that very end digits. Okay, so with approximate numbers, you've got something where we're keeping track of the precision, and we're trying to make sure that we give you as many digits as we think can be justified. With an around number, that's being thought about as kind of like an experimental measurement where there's a certain precision and we're saying it's roughly that number, and there's kind of roughly some sort of calculus of errors distribution around that. But sometimes you need to use approximate numbers to prove things. And so a way that comes up is, let's say we want a function and we want to say that we say that there's going to be an interval. Let's say we say something like this, and we say, here we go. So this will now represent a centered interval number. So this thing on its own is a centered interval, and that centered interval represents a number centered on 9.87 with an error interval of 10 to the minus 10. And the point is that now we support many functions which guarantee when you give it a centered interval, the thing it's going to give us the result is also guaranteed that the result will lie within that interval. So if you want to prove that something does or doesn't happen a particular way, then you can use centered intervals to do that. So it's sort of a way of it's a way of kind of making a proof of something that I'm afraid I'm going to. It's a way of making a proof of something. Just a minute. I'm going to do something to get rid of this crazy notifier thing that we're seeing. Hold on 1 second here. I think I have to go. Let's see if I can do better with this. All right. So here we've got, for example, a plot of this function, gamma of x minus sine x. You can kind of see that this function is between, let's say, 3 and 4. You can say, well, it looks like that function is positive. But let's say we actually make a centered interval we say, with x is that centered interval, what's the value of gamma x minus sine x? And the answer is we now get a centered interval centered on 9.2 with error 8.76. So this proves that that is always greater than 0. And if we say, is that greater than 0? It will say, yes, true, it's greater than 0. So this is kind of a new kind of number, a number that has a provable interval associated with it that can be used in all kinds of numerical computations. So that's another, it's kind of remarkable that there's that there are these kind of new types of numbers that we're introducing, just like when it comes to mathematical formulas, we have things like exact formulas, we have series, we have asymptotic series, etc. Okay, other kinds of math. We've also got, something that we introduced a couple of versions ago was complex plots. There's a nice function with some poles that got chopped off here. We can now ask, what are the poles of that function? This is something new in version 13.0, is the function poles, which goes and finds the poles of that function. And you can see it's given it in terms of algebraic numbers. These are exact algebraic numbers that we've got here. And we could go ahead and, if we wanted to, just evaluate that numerically to 50-digit precision or something, and we'll see the results. Okay, other things that are just practical pieces that are very useful. One of them is the ability to deal with vector variables in differential equations. This is just, we're saying that x of t is a vector of length 2. And now this is dealing with that as something which has a matrix in it. And that's a convenient thing. Another thing in the kind of differential equations area is the notion of so-called complete integrals. So partial differential equations, it's often very difficult to solve them, but sometimes there are particular solutions that you can get, so-called complete integral solutions that don't have arbitrary functions in them. They have arbitrary constants, but not arbitrary functions. So let's see. By the way, all these things, they're all very efficient things, that the way that around works is now very efficient. All these things are kind of down at the, we've been progressively improving the kind of optimizing with the latest optimization for the latest hardware and so on, all of the various arithmetic operations and so on. So I think we can say that that's very much a leading thing that that we've been able to do. All right, so now this is a more specialized function. Maybe I shouldn't even talk about it. Let's not go through this one here. Let's talk about partial differential equations, just to go through more mathematical kinds of things. So let's assume we define these variables here. And now we're going to do a computation in which a big thing that we've added is the ability to specify PDEs in a very kind of a symbolic modeling environment kind of way. So let's take a look at this. So we're going to specify the parameters, and we're going to, because we have all sorts of knowledge within our system of things in the real world, we can just say the material of something. We're going to be talking about a spoon here. The material of our spoon is silver, and that's something that our knowledge system knows about the properties of silver. Okay, so what are we seeing here? What we're seeing here is the specification of a collection of PDEs that represent solid mechanics. And so what's new in version 13.0 is the ability to specify. We've added a variety of things that go beyond the raw partial differential equation. This is an example of kind of a raw partial differential equation. We've added the ability to do things like heat transfer, mass transport, acoustics, with sort of special functions that represent symbolically those kinds of problem domains. So here we've also got solid mechanics, and what you see here is a solid boundary load value, and this is specifying features of the load with 100 newtons and so on, force with some fixed condition where you're holding the spoon. And now let's see if we can compute this. So this is now under the hood. It's doing a bunch of computational geometry. It's building finite elements. It's solving the finite element system. And eventually it should compute for us the result for that. And let's see whether we can, it's crunching and crunching and crunching. Okay, now the result is represented in terms of these interpolating functions. These are very useful things. I mean, I could pick one up if I wanted to. It's just a function. I know I could just pick up that function and I could apply it to, let's say, you know, some values, 0.6, 0.7, 0.8 or something. And if that's within the range of the spoon, it'll just give me a, okay. It'll just give me that wasn't in the range of the spoon, so it couldn't tell me the answer, but it would usually just be able to compute the value of that interpolating function. Now what I'm doing is I'm saying, and it's kind of remarkable one can do this, I'm saying this is a new function, vector displacement plot. This is the displacement function given in terms of those interpolating functions. And now I'm saying plot the displacement over a region that corresponds to the shape of the spoon. So this is now should be doing that. So it's evaluating those interpolating functions that we got as the result of the solving the partial differential equation. And then there's the result that shows the displacement of the spoon as we push it with 100 newtons of force, given that the spoon is made of silver here. So this is powerful stuff. And for example, we could say we could actually compute the strain in the spoon, because we've got the displacement represented as computable interpolating functions. We can compute the strain here. And so, for example, one thing we could do is we could find, for example, once it's computed this is usually, okay, so now we could say, find the maximum of the strain in that direction, the maximum over the domain corresponding to the spoon. And it's kind of remarkable. It's been like a 15-year or more project to build all the pieces we need to be able to do the geometry and underlying solving of all these differential equations and having them fit in the system to, in this case, work with optimization and so on, so that we can do things like this. So for instance, we could also say what are, let's pick a random point in the spoon. So this will give us, that's 3 random points in our spoon. And now we could do something like, for example, we could say, I wonder why it's set up this way. This isn't quite right. I should change this. This is, I should have said, well, anyway, apply that to, will work. It's just a little bit more obscure than it needs to be. What this is going to do is it's going to randomly sample 10,000 points in the spoon, and it's going to say what is the 3-3 component of strain at those points in the spoon, and this will now give us a histogram showing us that there's some kind of pinch point somewhere or something where there's a stress point or something, actually strain point, where there's lots more strain on the spoon than in most other places. So we have done a lot to kind of support what we've done in solid mechanics. This is just a big monograph that came out along with version 13. This is a monograph about validation of solid mechanics computations in our system. You can see it's a long description of how you validate the computations here, and these are test objects with success things and so on. We can keep going, and lots of detail here for doing kind of, I would say, sort of not to make too much of a pun on this topic area, industrial strength kind of solid mechanics analysis. Okay, next topic. So one thing we've been doing in recent versions is adding the capability for dealing with video. So one thing that's new in this version is that we have full support for being able to play a video directly in a notebook here. So this is some kind of test video. And we could take that test video and we could say, for example, we could say here something like, hope we can say here, come on, wake up. We could say something like video frame list of that video, and let's say 10 frames from that. And now it'll go ahead and extract 10 frames from that video. But now we can treat this video thing as just a sort of first-class object in our system that we do computations on. Here we just got images out of it. Okay, so another thing that we've done is we can take this video and I could make an animated GIF just by wrapping animated image around it, or actually probably just wrap animated image around these, and probably would make these into an animated GIF that I could pick up and put somewhere else. Okay, there we go. That's an animated GIF running around here. But we can just export that and put it on a web page or whatever else. Now, in version 12.3, we added the ability to make a slideshow video, for example, from slides, or to make a video where you're changing a parameter in something and creating a video from that. In version 13, we've added a number of other ways to basically create videos from things. So for example, one is what we call a tour video. So I could take that image, for example, and I could say, I think it's a huge image here. And I could say, if this wakes up here, come on. Oh, this is a very big image. This is what, because we wanted to show different pieces of the image. So this is a giant image. All right, I'm not going to leave this image in this notebook, because otherwise when I save it to the web, you'll also have a giant image there. Okay, so let's, okay, so here now we have that image, and we have this, we're making a tour video. So what we're doing is we're saying, show a tour of that image in which we show this position and then that position. And so now we can go and we can essentially, we just created something that will pan around in that image based on these two positions that we told it to operate with. So that's an ability to take an image and create from it a video. Okay, so let's now, okay, we can also do the same thing with zooming. Let's see how that works. We can take that same image and instead of, I know what's happening here. This has to do with the fix that I made for that silly notifier. I'm using a different source for these things, and that's causing trouble here. Okay, so now this is the same kind of thing, but now we're going to generate frames, and now this will get not only panning around in the image, but also zooming in the image, I hope. Let's see what that does. Oh, it didn't paste a different thing. Oh, that's no good. Whoops, I pasted the same thing. Wrong. Let me paste the thing that I wanted here. Oh no. It's what happens when you deal with these very huge images. Okay, let's try this one. This is showing a position and width. So those are two positions and those are two widths there. And now we're going to show how those vary, how to make a tour that varies between those things. So let's see here. So now we're zooming and then we're panning. And this is a way that you can take any image and kind of specify this different programmatic action. Okay, here's another thing. So just for fun, let's take, this is a image from the history of physics of a conference from 1920s. And we can go ahead and let's try and find the faces of people in that image. So we can do that using facial recognition. And this should give us, well, let's see what it found for the faces there. And it should give us, those are the positions of faces in that image. And now we can say, make a tour of those faces. Okay, so let's take this and we're going to make a shortest tour of those faces. And now let's take that original image and let's try and make a tour video that is based on visiting one face and then the next. So there's old Albert, and we're now walking around as specified in the tour, stopping on each face and visiting each face in turn in kind of a traveling physicist tour of that conference. Okay, other kinds of things we can do with videos. Here's another kind of new type of video, video generator. This is a grid video, and so here, hopefully, okay, there it's downloading videos from the cloud, and now what should be happening is this is now creating from 4 videos. It's now creating a video from a collection of videos. Okay, so here we go. So now we've got those 4 videos, and now we can play them all on a grid there. And this is all under programmatic control, so I could specify any configuration of these videos and so on. Another thing that we can do is to make what we call a snippets video, where you can take a video and then just show sort of the highlight reel, the trailer of the video. So here we're taking a video and we're creating snippets at particular locations in the video. And so now when we've created that snippets video, what should happen is that we'll see kind of a few moments of the video. This is just summarizing a much longer video by just picking out regions of the video around those points in the video. Okay, other things we can do, another new thing is overlay videos. So we can take a video and we can create an overlay. So for example, let's say let's just do this. Let's have a video here. I really don't think that should be called V. We'll say video here, and now we'll have a video that pastes another video in its corner. So let's go and see what this did. Okay, so now we have that video, and that's that little video, and now it's been overlaid on top of the video of the lemons and so on. Okay, another piece. So that was a little bit on video. Let's talk about images. One thing we added in version 13 is the ability to do image stitching. So here we've got a bunch of images that were taken around a scene from different angles. And now what we're going to do is try and stitch those images together. So this requires a bunch of different algorithmic kinds of ideas. But the result should be that we get a combined image. It might take a little bit of time and work to do that, but let's see what we get here. See if we can get a combined image from this. Let's try that again. Go ahead and so what it's doing is it's both lining up the edges of these images and doing some kinds of machine learning based sort of interpolation between edges of images and so on to try to deliver to us a stitched version of this image. At least I hope that's what it's going to do. Did that for me before. I don't know what it's doing. Okay. Oh, there we go. Finally came through. Okay. So it successfully took these different images, changed their projections, changed their perspective, and then stitched them together into a rather giant image here. So that's a new feature in version 13. Okay, onward we go. Another thing that we added in version 12 was the notion of trees. We now have, well, this is in I think it was in 12.3, trees as a basic construct. So we can say, you know, random tree 10, and that will give us a random size 10 tree. And this tree thing is a new sort of data structure, which if we look at what is its input form, it is a tree of tree of tree of tree of tree thing. This is a very convenient way of representing trees. That can immediately sort of flow between expressions and trees and so on, and graphs. So we can say something like a tree graph of this, and that will be a graph version of the same tree that can be used in terms of graph theory. A tree has a lot more structure than a graph, because, for example, one knows what the order of the branches coming out of a particular node are. Okay, so in version 13, we've added a bunch of new things with trees. Here's one, radial embedding of a tree. The generic tree would look like that, but we added the ability to radially embed the tree. Also, a bunch of capabilities for labeling and illustrating tree elements. So here, for example, we added tree element label. It's saying the 1/1,000th element of the tree should be blue, and all the other ones should be red, and that's the result that you get there. Another thing that is a big and complicated story is tree traversal order. Tree traversal order turns out to be a thing that's actually a very fundamental issue that has to do with, in the end, one could think about it in terms of reference frames in physics and all sorts of other things. But the question is, you've got that tree. If you scan that tree and echo which pieces you're visiting, what order will you visit the tree? So this is visiting the tree 5, 6, 7, 2, 8. So this is a depth first traversal of the tree. Okay. So for example, we could go ahead and write a function here that will explicitly number the elements, show the elements of the tree numbered according to in which order they were visited. So this is the standard depth first traversal of a tree. But there are other traversal orders that we can use now, and we have an option to the functions that scan through trees, like tree map. This is tree traversal order breadth first. And so that's then going first top element, and then it's going in slices like this. This is kind of like the an approximation to some kind of rest frame or cosmological rest frame or something in physics, that you're kind of looking at all the different elements of space-time. You're looking across space at a fixed time and then going down. Depth first order is something that doesn't get to happen in physics, except in very weird situations near black holes and so on. where you're kind of exploring one part of space first and then going back at subsequent times and exploring other parts of space. But from an algorithmic point of view, we are providing a variety of tree traversal order concepts like leaves first, top down. So that's and there are other kind of named tree traversal orders. And this is part of a much bigger story of a thing that I call multi-computation, which is a set of ideas that have really arisen from our physics project, but they're turning out to be very powerful and general ideas that relate to distributed computing and a bunch of kinds of modeling. Okay, talking about graphs. Another new thing we've added is graph coloring. So this is let's say you want to color the graph with no adjacent vertices are the same color. What colors can you assign to the vertices? There's the result. So we can go ahead and say highlight the graph with those colors. And so here we get that graph highlighted in such a way that there is a coloring of the graph where no adjacent elements are the same color. And that's something that's important for a bunch of algorithmic problems, whether it's register allocation in compilers or other kinds of things. This notion of graph coloring is more general than just actually putting colors on a graph. Here's an example where, okay, we're going to make a relation graph of the bordering relation for states in the US. So every node here is going to be a state in the US, and it's going to be joined by at least in the continental US. And I don't know, the people who know US geography better than I can probably say what that, oh, I'm just curious now. I gotta go figure this out. Graph vertex labels to automatic. I want to know who's that outlier state at the end there. Let's see, who is that? I should know this. Oh, Maine. Maine is I guess Maine is the only state that has only one neighboring state, New Hampshire, here. Okay, let's go back and say we want to take that graph, and now we want to find, let's see, we want to do an actual coloring of states in the US based on this. So we need to take the graph that we got here and find its coloring, find vertex coloring of that. And now we want to show that as a georegion value plot where each region of the US is colored according to the graph coloring from the adjacency of the states. So this is now a 4 coloring of the US, showing that in many parts of the US, 3 colors are actually enough, but you need 4 in a few places here. Okay. Let's look at another, another application of graph coloring is for things like tournaments. Let's say you have a complete graph, there it is. And let's say we can work out we can think of this as a tournament where people are playing tournaments against other people here. And we can say there are all the tournaments that have to be played. But now we can ask the question, if we find an edge coloring of this graph, that will tell us, if we're scheduling tournaments, that will tell us a way to schedule these things so that 2 people playing in the same tournament aren't playing in different tournaments. That 2 people are not playing in different tournaments at the same time. This graph coloring can answer that question as well. And we can ask, how many tournaments do you have to have? And the answer here will be 7. I'm now curious whether, I don't know, is this obvious that the number n, does it increase? How does it increase with n? Let's see. Let's go from 3 up to 15, let's say. Let's see what that does. Oh, that's interesting. Okay, all right, okay. So I guess it's even and odd numbers probably correspond to the number of elements one needs. I have to say I have a great urge to try one thing, which is to try and I wonder if we can do this. Okay, let's see. We now have a thing called a torus. And if we say, let's see. What is it called? I want to make a mesh out of this torus. I think it's a mesh region, right? of the torus. And then let me just, what I'm trying to get is the graph. Let's see. I think I need to look at the documentation. Always a good thing to do. Mesh-based geometric regions. So I think what I need to do is to find, okay, so I want to discretize a region, and then I want to find the, okay, so let's say I say discretize region for my torus. Okay, so there I've got a torus. And now what I wanted to do, I'm living very dangerously here because I wanted to see whether I can do a coloring of the graph that is on this torus, and see whether, and so now what I want to do is I want to actually get the mesh out of here. So what I want to do is to find the, gosh, what is it called? I want to actually find the mesh graph, mesh components, here we go. I want to find the graph that corresponds to this particular thing. So I think I want to find mesh. Let's see, do I want this or do I want some, oh, what do I want here? I'm trying to work out, maybe somebody can help me here. I'm trying to get the graph of, let me just see whether we can actually just search for this and see it. Oh, that's what I want. The mesh connectivity graph. That's what I need. Mesh connectivity graph. Let's see whether this is possible. So what this should be doing, let's see if this works, is for that torus. There we go. There we go. This is a pure graph. And that graph, we can count the number of vertices. And if we wanted to, we could probably, just to prove it really is a graph, we could say something like, well, let's just try saying, lay out the graph in, let's say, spring electrical embedding. And let's see whether that graph now it will give a different layout probably from that. Oh, actually ended up looking more or less the same. Well, if we did, let's say, radial embedding, I guarantee it will look very different. It doesn't, because we should have told it. It has its coordinates burnt in. I should have told it. Okay, just to prove that this isn't a fake. Let's go and use the spring electrical embedding here again, and let's see whether we can. So now there we go. So now there's our fake torus that was made just from the graph elements, just from figuring out what the shape should be, just from the connectivity of the graph. But now what I can do is I can say for this thing here, for that graph, well, either one of these graphs, doesn't really matter which one, I could pick that graph and I could say, I could ask it to give us the, how did I have the edge chromatic number of that graph. And that will tell us, okay, 9. If we say, what's the vertex chromatic number? I think that would tell us the, was the graph 2 before? This should, yeah, there we go. That's telling us essentially the number of colors that we would have to use on this torus, and it's different from the number that we would have to use on a sphere, and so on. So just a little bit of fun with those capabilities. Okay, another thing about graphs that we've done is to do things with planar graphs. So we can have a planar graph. Here's a planar graph. And now we could, for example, we can label the vertices on this planar graph. So let's go ahead and do that. And there they're now labeled. And now we can say, give me a planar face list of that graph. So that's going to tell us, now not thinking about this as a just free floating graph, but as something embedded in the plane, it's going to tell us what are the actual faces in terms of the numbers of the, in terms of the names of the nodes here. And we can also do things like we could compute the dual to the planar graph, where we take every face and turn it into at the center of the face, and we every face becomes a point, every edge becomes a face, and there's the result. Okay, another thing that is new in graph theory is subgraph isomorphism. Being able to see in that graph where are all the subgraphs that correspond to just a square, and we'll see those graphs being extracted. And that might be something you would say, who would ever care about that? But in our physics project, the whole evolution of the universe works by updating hypergraphs and by doing essentially graph isomorphism or hypergraph isomorphism to find where are the possible updates that can be made on those graphs. And so similarly here, if I wanted to, we could go ahead. Actually, I'm now very curious if we make, okay, let's make a planar graph. Let's make a random planar graph. Let's say we make a Voronoi mesh of a rectangle. That should make us, I think, a what did I do wrong there? Let me see. Oh, that's a points. Silly me. So let's just make a let's go ahead and make a, I just relearnt here, the mesh connectivity graph of the mesh region of a rectangle. Okay, so let's say mesh connectivity graph of mesh region of that rectangle. And so the silly. Okay, let's say of a disk, because that will be, I think, filled in. What is this doing? So I want to do something where I'm getting here. Let me let's see, discretize region of that, and that will give me that. And then I say mesh connectivity graph of that. Okay, so now I'm going to get the mesh connectivity graph of that, and that will give me my a collection of things. Oh, they're all triangles. No fun. I was thinking I would get something that wouldn't be all triangles, and so then I would be able to say find subgraph isomorphism on a well, actually, I could do that now that I think about it. I could find where is there a little. Let's figure out whether I can get a is there, let's say, a grid graph, let's say a 2x2 grid graph. That would be a square. Let's say a 2x3 grid graph. Is there something like that that is embedded in this graph here? So I can say find subgraph isomorphism, and I could say that's on line 43. So actually, I could just say find subgraph isomorphism, and I could take that thing and put it in there. And now I could say, well, let's just try finding a square like that. Let's find one of those. Okay, so there I found the first square in there. But let's just see if I make a grid graph. Let us just make a grid graph, a 3x3 grid graph, and 3x3 grid graph. And let's see whether that graph as a subgraph is available in that big graph. Let's see whether there's one of those. No, there isn't one of those. So maybe if I take a smaller grid like this, we will be able to find one of those. Maybe not. Maybe it's not possible. Maybe if it's maybe by having triangular, having triangular pieces. Oh no, there we go. There is one. Okay, so that's the subgraph from that big graph that has the form of those two squares. And I could go ahead and I could probably say, show me, I don't know how many there are, but show me, let's say, let's just get 10 of these things here. And this is going to now find, oh, there weren't 10 of those. So let's say, I bet it'll work if I say up to 10 here. Oh, that should work. well, it refused to do that. So I guess that if I say here, let's say 3, there weren't that many either. So there's only one of these. Maybe it has to do with the exterior of the thing. At least I think that's what this is. Yes, here we go. Okay, anyway, that was an example of using subgraph isomorphism. Here's an example. Let's get a piece of chemical data. Let's say we have caffeine, and there we go. There's our structure graph for caffeine. And now, for example, this was a good example actually. Now we can find within that caffeine molecule, we can find a 6-membered ring, a cycle graph with 6 elements, and there is our 6-membered ring in that. And just to prove that that it works for, let's just do this caffeine molecule and see if we can get that 5-membered ring. There it is. Okay, another new thing in graph theory is something relevant for analysis of the graphs of programs. So this is a very simple program. This is something studied in our physics project, a multi-way system. Notice that I'm using a resource function from the function repository here, but I'm mostly doing that to just get this graph. Okay, the notion is what's called a dominator tree graph. And a dominator tree graph is telling one what are the elements that are kind of below that thing. If this was a flow chart, what are the things that live below that element that are affected by that element? So here, for example, A affects this thing here, which affects this thing here. If you get to BBB, it affects all these things here. So this is kind of a graph of the sort of trickle down effect of one thing on another. And that's relevant if you're studying kind of processes, both human and things in programs. Okay, turning to a different area. One thing that we added in version, we've added in version 12.3 was spatial statistics. We've continued to fill that out. This is a spatial point data would be an example of it's a bunch of points that could be on the surface of the Earth, or it could be somewhere else in space. And now we can do things with that as spatial data. So for example, we might make a spatial estimate, what will give us a spatial estimator function. And at every point here, this spatial estimator function, if we say at value 1, 1 or something, it will now give us an estimate of the value of the function that is implicitly specified by these particular things. So imagine that you're trying to find out, I don't know, how much oil there is under a particular place on the Earth, and you bore a bunch of holes and you find out the answer for each of those holes, and you assume that there's some continuity to the amount of oil in different places. Then what this is doing is it's giving you, you're taking spatial point data, and this is now giving you a spatial estimator that can estimate, were you to bore a hole at some other place, what would be kind of the spatially interpolated value that you would expect at that place. And so we could take that estimator there that we got, and we could like plot that estimator, and now we're showing us for this, given the values that we have concluded here, what would the estimates be? Actually, what we should have done here is to color this according to the colors that are used there, and we would be able to see the points in those blue areas and so on. Okay, so there's a lot of detailed stuff about how we deal with spatial data. There are different kinds of models you can assume. We put in all the kind of standard models that people use for spatial data, and you're able to take those models and use them to compute, to do different kinds of computations. Oh, that's very strange. Okay, moving along. Well, we're about, I think I should speed up a little bit, and conveniently, our next subject is time. So one of the things that we've done in version 13 is to be more precise in our handling of time. And in particular, it's like when you have a point on the Earth that you might have a a particular point, let's say the position of the Eiffel Tower, and if we say what's the geoposition of that, oops, we'll get a particular position, but that position will actually have those are long coordinates, but to know what that position is in XYZ space, you need this datum that specifies how that maps onto the actual shape of the Earth and so on. The same kind of thing happens for time systems. And what we're doing now is to introduce this concept of a time system, which gives us kind of this way of indicating how we're specifying time. This is all a bit complicated, but it all has to do with the difference between time as specified by the rotation of the Earth, by when let's say a particular point in the sky is above you as the Earth rotates, and what time you would get with an atomic clock that is just measuring time independent of the rotation speed of the Earth. And so there's these are the times associated with the atomic clock and the rotation of the Earth. And if we take those two times and subtract them, we will find out that there's a 37-second difference between the time deduced from the rotation of the Earth and the time deduced from an atomic clock. And this is a whole subtle issue. And if we wanted to, we could actually look at the difference between the times from associated with the atomic clock and the rotation of the Earth. This shows variations of the rotation speed of the Earth over the course of time in the last 10 years or so. There's just a lot of subtlety here. When you specify a date range, you can specify a range of dates in, this is now in the atomic time system. This is showing the very beginning of the year, just a few seconds after the beginning of the year. And what we're about to see is that there's a leap second that was added to represent the appearance of these are the times for the atomic times versus the times from rotation of the Earth, and we can see that they're a little bit off. And so the year began at a different time, there are a bunch of subtleties here. In any case, the main point is that we've now got time really nailed down, and we can really accurately represent precise times. That's important for particularly things like astronomy and space purposes and so on. So that's another thing added in version 13.0. Okay, another area is in geographics. So here, what we've done is we've had geographic images for a long time. What we've now done is to make them so that by default the labeling is done in vector fonts. So that by default it's possible to get kind of crisp labeling on everything. The default thing so far is to have the background be done as a bitmap. So the edge of the wood of the forest here is done that way. But you can request, by using a different geo background, you can request that everything be done with absolutely crisp vector rendering of the graph of the map. And that's something over the next few versions we expect we will be progressively optimizing this, so that we're just using our own kind of graphics primitives to render everything. And at that point, you'll be able to see every detail in arbitrary resolution. So that's another thing that's coming. By the way, one advantage of being able to do things like separate vector labeling is that you can do labeling on any projection of the Earth. So that's not been possible before. and the labeling all just works. You can also mix background layers. You can say this is a case where we have taken, this is going to be a map of Italy, where we are taking a street map, we're taking a relief map with a certain opacity, and we're putting vector labels on top of that. And so now we've got the three things. You can see the terrain, you can see the streets, and you can see the vector labels all combined together. So this allows one to make very beautiful looking maps. Okay, next area, we're going to talk about geometry, and we're going to talk about some things there. So imagine that we have a bunch of points that were randomly selected around a circle. Question is, can we find the circle that those points represent, which was in this case the circle centered at the origin. New function region fit that finds fits of different shaped things to two collections of points. So for example, here's a collection of points in 3D that correspond roughly to a cylinder. And we could go ahead and say, make an actual fit a cylinder to those points, and then superimpose these things, and there we get the result. And so now we have fit that cylinder to that collection of points. And okay, another thing related to this is what we call concave hull mesh. So for example, here we've got a bunch of points, and as you can see, they arguably look a little bit like a rabbit. If you take that and you make a convex hull, you're basically shrink wrapping the rabbit, and you barely see its ears. That's a convex hull. There is a new technique that we have, which is a concave hull, where we are looking, not where we're trying to wrap the thing more closely, and there we have the concave hull of that set of points. Another type of way to do that it's not a unique thing to find when you're trying to sort of wrap a surface around these points. It's not unique. We have another method, gradient fitted mesh, which is another method where some of the ears got separated here, but that's a different kind of mesh with different characteristics. Again, fitting points to a mesh. Okay, another new area for geometry for us is computational solid geometry, CSG, and constructive solid geometry rather. This is now taking constructive solid geometry and taking the intersection of a ball and a cuboid, and we can go ahead and ask, let's say, something like, what's the volume of that? And now it's going to do a bunch of integrals, and maybe it'll give us a result here. Tell us okay, so it tells us the answer for that is pi over 6. And it did that by just working out the integrals that correspond to those precise regions. Well, now we can use the CSG methodology to make much more complicated regions. Here's a more complicated region. And again, we can say, what's the volume of that region? It should still be able to do all the integrals that are needed. And they might be rather difficult integrals. And just imagine trying to write down by hand all of the different conditions for all these different integrals and changing variables and all those horrifying things. It's been many decades since I last did that by hand, but it's still, you'd have to, before this technology, you would still have to go and try and set up all these coordinates and things and do the computation. I think it's going to finish in the end here. So let's let it keep running for a while and see if it can actually compute analytically that the volume of that strange shaped object. Let's see, is it going to do it? Is it going to do it? I think we just let's let it keep running for a little while. I think it's going to succeed. Although, as I said, it's quite difficult. It's very difficult for humans, and it's even difficult for the machine. I think it's going to succeed. But while it's thinking about that, let's talk about some other kinds of things. We have this notion of a CSG tree. So for example, one of these objects, we can think of it as formed from unions and intersections. This is an actual tree. We could, if we wanted to, we could look at the input form. We can't look at the input form yet. When this thing is computed, we can look at the input form. There we go. We finally got it. Okay, let's see what that is numerically. 1.93. Okay, it would have been easy to compute the numerical result. What's hard is to get an analytical result for a shape like that. So This is a tree, one of our tree objects, but it's a tree that has a collection of these geometrical forms in it. And now we can actually say, evaluate that CSG tree, like put all the pieces together and what we get is that part. And that's like what you would have in a computer-aided design system. You can do all kinds of useful things with it. Okay, another thing in version 13, congruent regions. We can ask the question, are two regions, let's say we rotate this rectangle, is it the same as that polygon? Yes, it is. Okay, and we can find transformation functions between, let's say, that rectangle and that polygon. So now we're finding a region transform. And so that's going to find us what we could see in this particular case is just a rotation matrix that transforms one object to another object. Okay, let's change topics completely. Let's talk about chemistry. In the last few years, we've been adding a lot of sophisticated chemistry to Wolfram language. So something we've done in this version, a variety of sort of cleanup pieces of chemistry as we start working on some major new chemistry areas. This is the ability to label a diagram with chirality. We could label all sorts of labeling of molecular diagrams. So this is a 3D molecule plot with atom labels on C and N showing their oxidation states. Okay, a new construct for us in chemistry is the notion of a chemical formula. So we've had the notion of a chemical diagram, but this is a chemical formula where we're not really saying where are the, these are just 12 carbons, 16 hydrogens, etc. It's just a formula. We could ask, for example, what's the molecular mass associated with that formula? It'll give us the result. More interestingly, we could say, show us, find us for this thing. Let's say find isomers, and that will try and find us actual specific chemical species that have that chemical formula. And so now it'll go and try and find in a variety of sources. You can tell it which sources you want to look at. There we go. So these are actual molecules that have that chemical formula. So let's pick a random such molecule. Let's pick one of the ones at the end here. And let's say something like molecule plot 3D of that. And hopefully this particular molecule, there it is that's that particular molecule with that chemical formula. Okay, another thing we can now do is to take molecules and make a feature space plot, use machine learning. We have a feature detector for molecules, so that was on line 97, and we could say something like make a feature space plot of the molecules on line 97. So now it's going to give us it's going to try and take each of those molecules, turn them into something that a neural net can understand, and then show us where in feature space those different molecules lie. And there's the result. So we see there are a few molecules over here, and then most of them, those are the particular molecules, most of them are arranged over in this section here. There's a good way to understand something about molecules. Okay, another big new structure which is coming is a structure called chemical reaction. And you'll see this built out over the next few versions. You'll see this built out in all sorts of different purposes. But here, for example, we can say, show us the reaction rule. This is showing how much of each substance was involved in this nominal reaction here. We could say reaction balance. I think we could just say reaction balance of this. And oh, why can't we do that? Oh, because we have to tell it's a chemical reaction. I see that we just gave it the rule there. So I can just say chemical reaction of this thing on line 101. And there we got the balanced chemical reaction with 19 oxygens and things like that. If I wanted to, I could go ahead and ask for the reaction rule again, and then go on computing things from there. So you can do very elaborate chemical reactions. You could, here's one that has some where you basically are solving Diophantine equations with integers, and this one has a 1399 in it, which is sort of a more exotic kind of chemical balancing. But so this is the beginning of a lot of work that we're going to be doing on chemical reactions and chemical synthesis and so on in the system. Okay, another thing we've added in the last few versions is biosequences. So this is a typical DNA sequence, and we now have biosequence plot, which is a sort of a standardized way of plotting genetic sequences. And we can do, this is now a plot that shows an RNA molecule in which we have added certain bonds, certain secondary bonds here between these things, and this biosequence plot will now show us what that looks like. And there's a sort of standard notation in, for example, the RNA world for specifying how things are sort of arranged, the dot bracket notation. We support that, and you can make images from that. We also support all kinds of elaborate things like hybrid strands with different kinds of, this seems to be a hybrid DNA RNA strand here. Is that right? No, that cannot be. Well, that's a, not sure what that is. That is probably assumed to be RNA. Not sure. Anyway, we support that. Oh, okay. Here we've got an actual molecule plot where we take that biosequence that we have there, and we actually figure out at the atomic level what are the actual atoms that would be in this. And if I knew my biochemistry better, I would know what all those different pieces were and what was the correct story here. So let's see. This is showing us cross-linking structure between two peptides, two amino acid chains, and there's the result. And this is again making use of our biosequence bonds in biosequences and so on. Okay, lots of kinds of data in the world. Another type of data that we have now in version 13 is flight data. Unfortunately, only for the US so far. We hope to get it for other places in due course. So that's showing us that there were 2 flights from Logan Airport in Boston to San Diego yesterday. Those are the 2 flights. And if we say, what are the properties of that particular one of those particular flights, we can say, what can I ask about that flight? And there are probably all kinds of things I can ask about that flight. So for example, I could ask something like, let's make a date list plot of the, let's take this flight, and let's look at the altitude. So the altitude, actually, if I just compute the altitude here of that flight, that will be a flight, and this is real-time data that we're getting, but this particular flight will be a historical flight here, and so we should have, oops, oh, I should have used this. You know, there's an argument. Well, anyway. Okay, there we go. So there are 411 data points there, and I could show the date list plot of those data points. And there I see the plane was gradually going up to higher altitudes as it probably burnt off fuel. Actually, we could probably just say plot range arrow all, and it will probably show us the whole flight going from ground level to ground level. Same flight, let's say that we take this, looks like it's the same flight, okay. We could take that and we could show the flight path of that flight in, okay, it's got to download a bunch of information here. There's the path of that flight. Or for example, we could do the following kind of thing. We could ask, where in the US did flights depart from Boston going to? So now it'll download all that data and show us a geoplot of the results of that. Or let's do something very ambitious. Let's try, see how long this takes. It might take a little while to download all the data and compute everything here. Should be able to do it. See, one gets very spoiled because after it becomes easy enough to have to specify to the computer what to do, then it's it could have taken a long time to specify this, and then the time it takes to get the result would have seemed like nothing. Well, let me show you an example here, pre-computed example of something else we could do, where we could take all the flights from Logan Airport yesterday in Boston, and we can show what were the paths of all those flights near the airport. And so what we're seeing here is a bunch of planes in various traffic patterns around the airport, showing we could probably deduce what the wind was like that day based on what the traffic pattern around the airport was like. Okay, moving along. I think I'm going to kill this off because I think we're not. I think it's taking a bit of a while to look up all of those different flights and so on. Okay. Another very requested. If I were to pick the most requested, some of the most requested kind of features of all time, multi-axis plots is one of the most requested features of recent times. And so you've got two functions here, and you want to plot them, and they're on different scales. And so here what we're seeing is the blue scale. The blue plot is relative to the left-hand blue scale, and then the orange plot here is relative to the little orange tinted scale over on the right. Now that's all well and good, but what happens if you have a whole bunch of different axes and scales and so on? How does this work? That's why it took us so long to implement this, is that we wanted to get all those kind of general cases right. So this is a much more elaborate case where we've got 5 different plots here, and they're all on different scales, and we're indicating here the scale for each of those plots. And if I wanted to, I can specify in great detail. I can say I want to put some axes on the left and some on the right and all that kind of thing. So here I've got this axis here is a combined red and green axis, that's purple, and so on. And then there's other axes here on the left. So this is sort of the general case of the multi-axis story. Another thing that's kind of being steadily built out is the idea of plot layout. This is going to make 4 plots, and it's going to lay them out in a grid, but it's going to optimize that grid so that it doesn't repeat the tick labels. It only shows them once, going above and across. Okay, another thing is okay. Here's another feature. Is the fact that dates can now be coordinates in all kinds of plots. So this might be a time series, which that's a time series of the uses of the word plot. And we can now just say list line plot. I have to remember that one can do this. It's been so long I've been conditioned to use date list plot, but now you can just use list line plot, and it knows that those things at the bottom are dates. So and that means also that among the scaling functions that you can specify if a plot is a date scaling function. So what this is now doing, this is taking values from a data bin, and it's asking the question when, and it's making both the overall date and the time of day here. And so it's plotting kind of a diurnal plot of those times of day for that for the things in that data bin. Okay, here's another weird, well, I say weird, this is another unexpected thing that we managed to make work, which is plotting with infinite range. So what that's doing is it's gradually scrunching up the plot to allow it to get to infinity, so to speak. And so, for example, we could say make a list of the first 1,000 primes and plot that in such a way that we've scrunched up both axes to get all the way to infinity. So that gives us some indication of how the sequence of primes is growing, assuming nothing too surprising happens towards infinity. And we can see if we're making a plot of, let's say, these three functions, it's useful to see that infinite range because we can kind of see that one function always lies between these other two functions. Okay, more on visualization. I showed you earlier vector displacement plots in 3D. This is a two-dimensional vector displacements plot where you're showing as a function of position in this annulus how that annulus is deformed. Same kind of story in 3D. This is showing how a sphere, if you are specifying the coordinates of pieces of a sphere, this shows how that is being deformed under that transformation. We have a vector version of that. We also have a version of we introduced geograph plot in the previous version. This is geograph value plot, where you can show kind of the amount of flow between cities, for example, here. Okay. Let me talk about another thing. In 3D graphics, we have had the idea of lighting 3D graphics from sort of the beginning from version 1, 33 years ago. We had this idea of simulated lighting. But now, so that's with our default simulated lighting. But now we have the idea of making a symbolic specification of lighting, where we can go ahead and say, take this and make its lighting. We've always been able to specify lights in kind of basic lighting, but this is now specifying light symbolically. So there's an ambient light, the directional light, there are the directions, and now we've got this kind of green tinged thing that has been lit with these symbolically specified lights. And one of the things we can now do is to include lights as something that is local to a scene. So we can include them as part of a style. So there is different lighting for the sphere and the cube in that scene. And so if we do a more extreme version of that, using that torus primitive that I showed you an example of earlier, this is showing us, okay, this is showing us for each one of those toruses, each one of those rings, we get a different appearance based on a different different directional light that's been used to light each torus. Okay, let me show you another thing. We're going to talk about machine learning now. One of the things that we've done in machine learning, we've had for a long time these functions like classify and predict that try and learn from examples what something is. But the thing that you're learning from example about what it is a whole thing. Like it's a picture of a cat and nothing but a cat, or a dog and nothing but a dog. What we're doing in version 13 is to add the idea of a content detector function, which allows you to find subpieces of something. So for example, let's say we do something like here, I ate cranberries while watching tennis. Okay, so this is picking out, that was just picking out one thing here that picked out tennis as a sport. Now it's a little bit non-trivial that it could pick out tennis as a sport because the training example I gave it only talked about soccer. But what it's doing is it's using the large corpus of existing built-in knowledge and existing trained neural networks to be able to generalize from the particular example that I gave here. So now another example that I can give, this is a case of training a visual content detector. This is a considerably more difficult thing to train, and this training takes about 5 minutes to do on a GPU system. But if I just take that detector and let's see if I can just pick up that detector. I'm not sure I will be able to. If I can, that's a bad sign that it says data not in notebook. Well, were I to be able to pick up that detector, I could do something like this and find from that image where in the image these subparts that I taught it here occur. Or I can be more elaborate and I can have a, there are different things that the content detector can pick out. So it can pick out, for example, legends and bounding boxes and can indicate what I've seen there. Okay, also in machine learning, we have a variety of new ways to indicate sort of how machine learning, what was important to the machine learning system when it came to a particular conclusion. Kind of the explainability of machine learning, we have a variety of things along those lines. All right, I'm not sure, let's see, we have another example here that maybe I'll just give you a very quick walkthrough of this one because it's kind of complicated. Let me try and find my way to it. Let's see. We've had for a while now, a feature of Wolfram language is the ability to deal with control systems. This is now part of the general story of control systems. This is for tracking, being able to make a control system that tracks something you specified. So for instance, here's a robot. There's your toy robot, and the goal is to make the robot track a particular path. And here we have a model for the robot represented in our systems modeling language. And that model, we're now going to take that model, which is a sort of physical model for the robot. And what we want to do is to make the parameters of that model be such that when we feed in a particular input here, the drawing pen of the robot will follow a particular curve. So we can specify the curve. There's a curve we want to specify. What we're going to do is to try and build a controller. And this is a whole elaborate story of control theory and pole placements and things that is trying to build a control system that we can put in the robot that will make it draw the picture we specify. So now we can say, let's go ahead and we've built this optimal controller. We now try to simulate the device. And what we can see is it didn't quite manage to draw the picture we told it to draw. It had a little bit of a glitch, but otherwise it was successful. And so this is something that's important in, this is important for robotics and important for, well, other kinds of systems where you want to specify a particular thing to happen. And this is trying to say, given the actual mechanics of the inertia of the system and the way that it has the force that can be exerted here and there, can you achieve that trajectory, and what is the best way to achieve that trajectory? So we now have the capability of dealing with things like that. Okay, so let me move on here. I talked a little bit about the bracket matching kinds of things, and yeah, I want to mention that one of the features. Let's pick a function here where I can kind of bracket through it. Okay, so here, for example, let me go ahead in this thing, and let me add something here. Let's say I don't know. Let's say one arrow list. Oops, one arrow list. Okay, notice it put in the double brackets, f of x, y, etc., etc., etc. Now, I can always use control space, control space to exit that region. So I keep going. If you can see my cursor, I just went on, I went on, I went on, and now I'll jump to there. So control space is a way to move around, just like I can multi-click here. I can also use control space to progressively move more and more levels of bracketing out. And you'll see it turns green there because it's showing me what brackets I am currently in. And when I actually press control space again, you'll see a little black thing flash up that guides one's eye to the place where the actual next sort of bracket position is. Okay, another thing we've added is it's a big project to put progress indicators into as many of our functions as possible. So for instance, here we've got, oh gosh, this is going to do something horrifying. This is something which is now what's showing us progress here of launching a bunch of parallel machines. I have a bunch of machines that will need to get launched here, but then once those are launched, it will show us kind of the progress of our parallel computation as we go ahead and do it. And you perhaps saw some of those when I was processing videos earlier and so on. And you'll see different kinds of progress monitors, some of them very custom progress monitors that show you different details about how some operation is working. And there are a variety of ways. There's a new a global thing, dollar progress reporting. It was so quick. It was so quick. We could barely see the progress monitor there. Let me just, for the heck of it, let me just make this, oh, I don't know, make that 50 or something, and maybe, oh no, it was too fast for our progress monitor. Well, anyway, things like progress reporting is a global thing that allows you to switch on and off progress reporting. That's that. Okay, another topic. Let's talk about Wolfram Alpha notebooks. You may know that there's a new product that we have called Wolfram Alpha Notebook Edition, which is intended as kind of an interpolation between Wolfram Alpha and Wolfram language. And the idea is that you enter natural language, but your computations can be done built up in a notebook. Now, you also, within a Wolfram 1 or Mathematica, you can also get a Wolfram Alpha mode notebook. And here it is. And in this notebook, I can go ahead and say things like, what is the integral of sine cubed x? And I can use natural language to enter it, but then I get the Wolfram language echoed back here, and I also get the result that I can then go and do computations on. Here, should open up that bar, I can say, let's do the integral again. Let's try the integral again of that, and I get the result. And so this is our kind of natural language interface version of access to Wolfram language. Some things that have been added. This is something which actually you've probably seen in Wolfram Alpha. This is just a palette for letting one enter common operations, common mathematical operations. You can also, this is a palette used for entering those things into a natural language system. There's also things where you can directly get from the system. You can say, I don't know, plot sine AX varying A, let's say. Let's see whether we can do that. So that will now generate for us a manipulate that was just created. Oh, it actually didn't. It figured out, it decided that was A times X. So I might actually have to put parens in there. Now I just hit enter, and then it'll get us this. And now we can then vary that. And this was created from natural language, but there is the Wolfram language code, which we could then use and copy and paste somewhere else and use. Oh, that was it pasted a, I should have told it to use the, there we go, there's the wolf there. And we can tell it to paste the Wolfram language code and use it elsewhere. Okay, another thing we have in Wolfram Alpha Notebook Edition is direct access to our demonstrations project and to various kinds of new starting points for learning this. We also have a new thing here primarily intended for the Wolfram Alpha Notebook edition itself. This is a interactive quiz. Let's see, quadratic description plot quiz. I don't even know what this is. All right. So this is a thing where plot the polynomial with y-intercept. I have no idea how to do that. Well, okay. This is a neat thing. This is included in Wolfram Alpha Notebook edition. And probably I could learn to sketch curves this way too. Talking of quizzes, a big new thing in version 13.0 is the ability to make quizzes conveniently. Okay, so this is all a bit, it's a bit of a long story because let me show you an example. This is a deployed quiz. So this is a cloud notebook, and this is a quiz where I can type answers in here. Let's go ahead and make this a little bigger. I can type an answer in here, and it will say, if I say submit, it will submit that answer. I'm surprised this is, oh, I see, I have to probably submit all of these at the same time. They've probably been set up that way. Oh, no, I didn't. I put a check mark there. So if I say here 2010, submit it, it'll say no. And then I could resubmit it perhaps here if it's been specified that way. And it'll hopefully say yes. And so this is a quiz that was created in Wolfram language and deployed to the cloud. So how was that created? Well, turns out it was authored in an authoring notebook, and let's pull up that authoring notebook here. Here's the authoring notebook. So this is, you get to this authoring notebook by saying new programmatic notebook. And this is, where is this coming from? This is, this from Form Authoring Notebook? No, that's Form Authoring Notebook is something more general. I guess you can say create new notebook of a quiz notebook, but I'm surprised you can't get it from that menu. Okay, but in any case, this is something that is a form notebook okay, maybe I should start a form notebook here. New programmatic notebook, form notebook. It's a Q&A form notebook. Okay, I don't know how to get those from the menu. I'm surprised they're not in the menu. They should be probably. Maybe they will be in the future. All right, so the idea is this is a symbolically specified thing, a question object in which, I don't know why this is done with a string. That seems like the wrong thing to do. One could do that with perfectly well with an integer. But in any case, this is something which shows us the code. We can make a preview here that shows us what that question will look like if it is previewed. Why is it done that way? I have no idea. It should be done with an interpreter. Okay, so here's another thing where we look at a preview here, match one input with one output. So this is a date list, and we're matching it with various other dates here. And so this is one of a variety of different kinds of elements that you can put into a Q&A form notebook. And then what you do is to say, generate the Q&A form notebook. So there's a way of specifying what you want the parameters of the generated notebook to be like for example, where you want to put the answers that people are submitting to it. Okay, it's now actually generating it. But when I tell it to generate, it will produce a cloud notebook that is then a deployed version of this Q&A here. We should, actually, I don't think these should be fixed. I think these are, we can do better in terms of the questions we're asking here. Okay, so I just told it, I actually told it to generate it twice, which was a mistake. But anyway, this is now generating, as it happens twice, a version of this directly in the cloud that you can then interact with. Okay, so this is part of our support for kind of quiz-like things and things for education along those lines. All right, let's change to a completely different topic. Oh, that was the, okay. That was a piece of an authoring notebook that we didn't look at now. And right, okay. The main point here is that if you want to make a quiz, this is an incredibly efficient way to do it. You can also do it programmatically, but you can do it using that GUI. And it has sort of all the power of the ability to, for example, have people enter pieces of code and be able to compare those pieces of code. We did that for my elementary introduction to Wolfram language. The ability for people to enter code. This is taking that technology and making it available to everyone. Okay, let's see. I can probably show this. So this is now a completely different area. We're talking about imports of things. So this is now importing an mbox. And so this is showing us the thread graph of a mailbox. So it's showing us mail messages that were threaded, how the mail messages were threaded together. Something I'd never seen before, but it's an interesting, interesting thing to be able to see. Okay, let's take another example here. This is another new capability in version 13. We had added the ability to import PDFs as sort of faithfully as page images, but now in version 13, this is now a pure vector image, pure vector data. So for example, and I'm sorry, that's it being imported as as page images here. But now what we can do is to say the same thing for, let's say we want page graphics. We'll want one of those pages not as a bitmap image, but instead as graphics. And here it is as graphics, and I can kind of prove it's graphics by, if I wanted to go in and click, 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 I could actually edit this and go and change. There we go. I'm now making the ink smear in this graphic. And even these individual font characters are all just vector graphics that I could smear if I wanted to. So this is really gives us the ability to take PDFs and treat them as data that we can manipulate. Okay, another completely different topic, CloudExpression. So if you want to make something where you're dealing with a bunch of persistent data, but you want to access, you want to kind of peek and poke at this data. You want to just make data that's, and you can do that by making a cloud expression. Cloud expressions are persistent. They're stored in your cloud account. And you can take a piece of that expression and it will just come directly from the cloud in here. You don't have to import the whole expression. If you wanted to, you could say get CE and it will get the whole expression. But if I wanted to, I could say CE of 5 equals hello, and then that will be modified in the cloud, and CE of 5 will be pulled from the cloud to be hello, but none of the rest of that expression got modified. It's kind of like an expression database in the cloud. And this is an important thing that we actually introduced cloud expression a few versions ago, but what's happened in version 13 is it's really become a robust place to store data up to the tens of megabytes type range are conveniently stored in a cloud expression in a way where the individual parts of the data don't have to be imported into the in order to get used. Okay, another area that we has advanced a lot in the past, since the past version, is the function repository. We now have, in our function repository, we now have about 2,300 functions, and there are all kinds of interesting things there. The function repository is a great place to find kind of specialized or sort of ahead of the curve functionality that hasn't yet made it into the main system and might not for years to come, but the function repository has versions of that. And what's convenient here is I could go, let's say I go to something here, I know what some of these do. Let's say I go here to multi-way combinator, I can just click this, I copy it, and I get something which is referring to that resource function. Now I can compute with it, and that's how it works. And for example, in documents that I write now, when they need sort of additional code, we're really trying to package that code into the function repository so that it's readily accessible to people. And so in general, you can say, here's a resource function Venn diagram of this XOR thing there. It's just now using that code from the function repository. Lots of useful things in the function repository, lots of things that are a bit specialized, like for example, let's see what happens if I do this. If I say, show me graphics for a sports field. Okay, that's tennis. Let me try, I don't know, soccer or something here. Okay, well, it's cool. But clearly something a bit specialized for our main system, but something that's very useful if you need it. Well, here's another one that's kind of fun. This is something which will try and use image processing to render a plot using some kind of pseudo handwritten, I think it might take a little while to do this actually, but kind of to make a kind of pseudo handwritten version of the plot. Okay. It's probably grinding, trying to imitate the actual handwriting of this plot, and it's taking a certain amount of effort doing that. Okay, let's talk about the next area while it's thinking about that. Let's talk about Paclets. Paclets have been a mechanism for delivering functionality to our system, not just functions like in the function repository, but all kinds of things, whole clusters of functions, things in palettes, all sorts of different things that perhaps are binary programs in some external language, whatever else, all sorts of different things being able to be delivered in a Paclet packaged together. And we've used Paclets for quite a number of years to deliver functionality between major version releases. We've been able to field upgrade lots of functionality. Okay, so we are introducing an increasing collection of Paclet tools, and you can use, okay, I'm going to do this. This is kind of a bad idea, and I have to remember to clean this out. I'm going to create on my desktop a Paclet, and that will show up somewhere on a desktop in my desktop files, and I can then see that. This is kind of like creating a project. Oh, where is it? I don't usually go to my desktop. Wow, there we go. My Paclet is on my desktop. Well, fancy that. Let's see, how do I get to this? And what you'll see in my, I don't know how to make this bigger, I'm afraid. I wonder if there's a magnify window. View, maybe View has it. Nope, not a thing anybody thought about, how to make the Finder bigger. But anyway, you probably can't see this, but it has a documentation folder, a kernel folder, and a pacletinfo.wl file. And the idea here is that we can create a Paclet that has, we can specify components from the Paclet. Once we've created it, we can then just drop files into our layout, and they will automatically become part of the Paclet. Then you can deliver that Paclet and set it up so that it can be installed, and so it can make use of the whole Paclet mechanism. Another thing that has been introduced is the notion of Paclet symbol. So if you have a Paclet that's been deployed and it has some symbol that's mentioned in it, just like you can say resource function to kind of deep reach into the function repository to get a named function out of it, so Paclet symbol allows you to kind of deep reach into a particular specified Paclet and kind of pull a symbol out of that Paclet to be able to be used elsewhere in the system. So it's kind of instead of installing the Paclet and then being able to use the symbol as a generic Wolfram language symbol, Paclet symbol allows you to kind of deep reach into the Paclet to be able to get that symbol. Now, another thing that's been increasingly found, but being built, is documentation tools. This is our mechanism for allowing people to write documentation using the same technology that we've used for many years. So I could create a new function page, and it's probably going to insist that, it's probably going to tell me I have to put it in some directory, et cetera, et cetera, et cetera. But it's then going to create, actually, if I do that and I say ignore that, it'll probably create a new function page. This is now what I need to do to create a page that will be built into documentation, just like the documentation that we have. Why is this saying new in? Oh, it must know I'm me, because that's a header for built-in system functions. That shouldn't be part of this this system here. Okay, but anyway, so you can just build given that you've created a bunch of documentation as notebooks, there are functions now to build that documentation into something which can be deployed with the Paclet. Once you have Paclets, there's a mechanism that is useful and important, which is what we call context aliases. So, for example, if we were to explicitly do something like needs computer arithmetic, we could then refer to the symbols in computer arithmetic by their names. But if we didn't do that, we could do something where we say, this is a new thing of context aliases, needs computer arithmetic, but we're aliasing the context computer arithmetic to CA. So now a function that is in the computer arithmetic context, like a function like ulp, we can now reference by using this context alias. If we did it with needs, the whole computer arithmetic context will be the context of that particular symbol. But here we're saying reference that symbol using this alias for the context. Okay, I think perhaps one of the last things I want to mention here, something that we are working increasingly towards, is symbolic web pages construction. So being able to specify directly in Wolfram language a web page that you want built. So here I'm publishing a web page that has a web column, and it has first, second, third column, and it has various items. And now I just published this to this web page, and here it is, and it'll behave just like a web page here. But I specified these things directly as a symbolic web page specification. Now, an important feature of this is a new function called interface switched. Interface switched is something which will build a web page, but then as part of, in its deployment, it will, in the CSS of the web page, be able to switch certain parameters depending on the width of that you have made the page in a browser. So for instance, let's do this. Let's say I make a web page in which I just interface switch on the width of the page, and between 0 and 480, I show a little tiny pussycat here. Between 480 and 768, I show a tiger, and from 768 to infinity, I show a lion. Okay, so now what will happen is that will deploy a page, and when I have this page, when I have that page wide, there's the lion, If I make the page narrower, the interface switch will kick in and it will go to a tiger. If I make it smaller, it'll be a little cat. So this is just you can embed interface switched anywhere in the symbolic specification of your web page, and it allows you to do responsive design for web pages. Okay, so lots of different things that we have been doing. Among many areas that we've been working on are areas around blockchain. This is an example of a, let's see what this works. This is we have now all of the ability within Wolfram language to mint NFTs. And this was an NFT minted on the Cardano blockchain and has probably gone out of circulation now. It probably hasn't been stored for long enough on IPFS. But it was, had it been there, and this is one feature of storing, the blockchain stays forever, but things like IPFS don't. Apparently, this is the image that you would have got. Were that image still to be there on this blockchain? But the transaction data associated with, let's see, the blockchain block transaction data. Yeah, here we go. Should be that transaction should have its data. There we go. So this is for all time stored on this blockchain, the Cardano laser eyes on the Cardano blockchain, and it has certain features stored, and then it has a pointer to this IPFS thing. That IPFS is one of the storage systems, along with S3 and some others, that we can access directly from our external storage function. So that's a bit of a summary of things that are new in version 13. I will say, and let me actually just publish this notebook to the cloud. It may be a very big notebook, I'm not sure. Let's publish this notebook to the cloud so that you should be able to get access to it and play around with the things I was showing here. But now one thing I want to mention in terms of uploading and downloading and so on, one of the things that we've done in version 13 is to make a sleeker version of downloading our system. So you're downloading Mathematica, Wolfram 1, whatever, there is now the possibility to download it without documentation. So our documentation has been getting ever bigger as we say more things and have more detail and so on. And it's about, let's see, I think it's gotten to maybe 5 gigabytes or something, including all documentation. But what we're doing is to slim that down and get it to the point where it is a less than 2 gigabyte download for the actual for the actual executable, and then you can set it up so that you just download that sleeker executable, and then the documentation is all accessible on the web. Or you can always say, okay, now I want to download the documentation, which is another 5 gigabytes or something, that so that you can have it locally on your machine. But so this is just a way of making it more convenient. And actually, when it comes to Wolfram Engine and Wolfram Engine for incorporation in other systems, we are getting sleeker and sleeker versions of Wolfram Engine, and it's down to a couple hundred megabytes that is required there. So, I mean, it's the download size of the engine is still a gigabyte, but there are sort of slimmer versions of that we are developing. All right, well, I think that was pretty much all I was going to show here. And I don't know how long I've been yakking on, but oh, there we go. Look at this. You see, for when there were in-person events, this was a very convenient thing. You do this, you put up this, you publish the notebook, and then everybody sitting there can take out their phone and look at the QR code. And we got this feature in there just before a pandemic, and nobody did anything in person. But now we can actually send out the link to this. Okay, well, let's see. We have some questions here. Let me see what I can address. There was a question here about progress on theorem proving. Funny you should ask that. I was just working on things related to theorem proving just yesterday and trying to understand the relationship between theorem proving and a lot of ideas that we have about multi-computation and so on. I might be able to show you a thing that doesn't exist yet. Let me see whether I can show this to you. And let's see whether I can find a version of this. Let me show you something. This is, if you follow the physics project, you might know about things called token event graphs. And a proof is actually like a token event graph. And so here's a proof represented in a different form. This is showing a hypothesis, and it's and what it's showing is every one of these events is combining two statements by substitution, in this case, to produce another statement. Anyway, the end result of all of this is that we are going to have some very interesting capabilities for representing proofs. That's been one of the big challenges, is how do you represent a proof? We're now getting ways to do that. All kinds of ideas about proof-to-proof transformations and so on. So a lot of very leading edge stuff happening there. There's a question here from Satiros about integration with biological databases. We already have a lot of that stuff. I mean, into things like GenBank and OMIM and so on. I don't know, and our service connections provide additional kinds of access to additional kinds of APIs and so on. Let's see. So we may have some things here that are relevant to that. If not, we'll take it as a suggestion. These are all external APIs that are services that you can. These are connected services. We also have integrated services where the things are directly integrated. So, for example, if I say GeoImage, that's an external service. If I say GeoImage of a geodisk around, I don't know, the Washington Monument, and let's say, that's interesting. Park. Okay, let's just try a 1 mile radius around there. So we get something from this. No, it didn't give us because it's a class of things. Oh dear, there are multiple Washington monuments, I think. I think I should have actually read what it said. Anyway, never mind. We can, but this kind of imagery is coming to us by a connected, integrated service. There are other things which are more weakly connected. The question here is there support for 3D neural nets? What is a 3D neural net? Neural nets are always, I mean, they're arbitrary tensors, so they don't have any particular dimension. Not sure what that means. If that means a 3D convolutional network, the answer will be yes, because we have 3D images. And you can have if I take some, so I think it depends what that question means, I don't know. Question from Ron, development of elliptic curves, order of elliptic curves and so on. We actually do have a bunch of work going on elliptic curves. It didn't make it into 13.0. It will be coming soon. I think we added some, just not really what you're asking, but we added some new kinds of elliptic curves useful for cryptography. But actually, the further support of elliptic curves in cryptography drives the need to support more elliptic curves for mathematical purposes, and that is coming. let's see, there's a question or comment here about supporting Apple Silicon. Does version 13 add support for the Apple Metal GPU backend for GPU neural net computations? The answer is, I believe not yet, but it is something actively being worked on. And so that is something that we can deal with. Oh, I'm being told here that actually we can represent external those identifiers for external. Let's see, what is this? Okay, so these are different kinds of external identifiers for things like genes that we support. And so, for instance, well, somebody should have helped me out here, but I think if I say external identifier entree gene ID, this is a way of being able to represent an external. If I knew what to type here, I would be in better shape. This is a way of representing an external. Here, let me show you an example. Let's pick a chemical, let's say TNT or something, and let's ask for. I wonder whether I can ask for. Let's see. How do I ask for external identifiers here? Let's see what our properties of this are. Oh boy, so many properties. I could ask for, here we go. No. Somewhere here. Ooh, look at that. There's a problem there. A horrible problem there. I might be able to, I don't know what any of these are external identifiers. I don't know what some of these are. So, but if I put that in there, I might get one of these external identifier objects. No, I didn't. Well, let's say if I said Wikipedia data, Wikidata, and I say, what can I say? Something like an ocelot here. What I will see, oh no, I want to get, let me get our own ocelot entity. And what I should, why am I not seeing anything there? Don't I want to get, oh, that's right. I need to, yeah, okay. This is what I'm going to show you. This is a Wikidata external identifier. That's the external identifier for the moon in Wikidata. And if I show what is that, this is the kind of external identifier it is. But we can now, I think, probably identify that that is an entity of ours. And let's see what happens if we say, if we ask for, okay, we can ingest that as an entity of ours, and we can ask for properties of this. Similarly, for these external gene identifiers, we can do the same kind of thing. So we reference it using an external identifier, and then are either able to pull information from that external source or already know that information. Okay. Let's see. Question from Soren about processing math images with math OCR. The answer is that is coming, not here in version 13, but coming. Actually, we worked on math images a very long time ago and almost released them a very, very long time ago, and then didn't because we didn't think there was enough interest in them and they were not high enough quality. And we're now at the point where we think we can do that. Question from Transplexity, when are we getting graph neural networks? I believe there were some advances in version 13 along those lines, but the big advance is coming in the next version. Lots of work going on graph neural networks there. Let's see. A question here from Ali. How correct do we think that integrate is after version 13? Boy, we think it's pretty correct. I mean, you know, we run zillions of test examples. We've ingested all of the standard handbooks of integrals and all those kinds of things. Correctness is not really so much the issue anymore. What's the issue is the form in which the answer is given something which people say, oh, that's nice and elegant answer, or is it a big, horrible mess involving functions you've never heard of? So that's really the challenge there. All right, well, let's see. Are there any further questions that we can address here? Otherwise, please download, go to the cloud, use version 13. You can you know, pick up some random thing here and go to the cloud version. I could go here and just go in the cloud, and I could paste that in, and hopefully in the cloud I will get the very same thing, except for some reason it is pink there. Terrific. Well, it should work. It almost works. You can see it behind the pink, but we should be able to get. By the way, I should explain in terms of all these things. I think I personally have a unique ability to find problems in software systems. It's yeah. Okay. Well, there are no further questions. Then please enjoy version 13. We are already doing design reviews and live streams associated with the upcoming version, I think we can wrap it up for now, and I look forward to seeing you all on other live streams, maybe other venues in due course. And I hope you enjoy the results of what we've been able to deliver in the last 6 months in version 13.0, and in general the things that we've delivered in the last couple of years, going from version 12 to version 13. We are continuing to energetically push forward. We are pleased to get suggestions of things people would like to see implemented and added to our system. We also will be doing some things talking about bugs and limitations and so on. We'll be doing some public discussions of those kinds of things. And so if there are particular areas you think should be high priorities for us, please let us know. But for now, bye for now.